This is the structure of dihydroxyacetone phosphate. Okay, so the next step in this process is we take this dihydroxyacetone phosphate, and we convert this into fructose 6-phosphate. So what I'm going to do is I'm going to convert G3P, glyceraldehyde 3-phosphate, glyceraldehyde 3-phosphate, and DBAH, which is short term for dihydroxyacetone phosphate. So I'm going to convert this into fructose 6-phosphate. And I do this in the presence of an enzyme. It's called aldolase plus 1,6-biphosphatase. It's called aldolase and 1,6-biphosphatase. I'm going to take biphosphatase. Okay. So we do this in the presence of these enzymes. So we convert G3P, glyceraldehyde 3-phosphate, and dihydroxyacetone phosphate into fructose 6-phosphate. This is the product of the next step. So let me write down the structure of this. I think most of you know the structure of fructose. The structure of fructose is very similar to glucose, but remember, glucose is not an aldose, it's a ketose, so has the same configuration except for the ketose part. So this is the structure of fructose. So what's the structure of fructose 6? So this is 1, 2, 3, 4, 5, 6. So what's the structure of fructose 6-phosphate? So this on phosphorylasis, introduction of phosphate group. Okay, phosphate group introduction at the 6th position. So this gives you fructose 6-phosphate. This looks like the following. So this actually forms a phosphate bond right here in the presence of this H replaced by H2PO3, P double bond O, OH, OH. So this is phosphate, fructose 6-phosphate. The mechanism for this reaction is beyond the reach, beyond the scope of the discussion. So you get this particular product. So again, what we do is basically, so let me talk about the next step. So this F6P, which is fructose 6-phosphate, what I'm going to do, I'm going to remove 2 carbons from this fructose 6-phosphate. I'm going to remove these 2 carbons by an enzyme called transketolase, giving erythrose 4-phosphate. So I'm going to remove the 2 carbons are removed from this fructose 6-phosphate to give you erythrose 4-phosphate. Okay. So let me remind you the structure of erythrose before doing that. So what's the structure of erythrose? If you understand this, erythrose is what? Erythrose is an aldo. It's an aldo. It's an aldose basically. And more specifically, it's aldo. It contains 4 carbon atoms, so it's called as aldotetrose. I'm sorry about that. It's an aldotetrose. So erythrose is basically an aldotetrose. So how do you get erythrose? That's okay. So let me remind you that. So you can derive everything by going back to glyceraldehyde. So this is the structure of glyceraldehyde. Okay, so this is the structure of glyceraldehyde. So if I add a carbon, so if I add H and OH to this becomes erythrose and 3 O's, right? So you get, if you add, okay, so let me do that. So I'm going to add this carbon, so it's going to be HOH, HOH. So this is D-erythrose. I'm just drawing the Fischer productions of this. All right. Okay. This is the structure of D-erythrose. All right. So I'm going to convert this fructose 6-phosphate. You see this fructose, this entire structure, and this is converted to is converted to erythrose 4-phosphate. Okay. So I'm going to convert this into erythrose HOH and HOH. CH2O. This is just a degradation. What we're doing is basically we are removing these two carbon atoms. You understand that? The rest of the structure is just the same, but it's converted to aldose and other things. Okay. So this is called E4P because it's an erythrose salt. It's an erythrose 4-phosphate. This is called F6P. Fructose 6-phosphate. Okay, so this is what we did, and what next? So next step is the conversion of E4P. We're going to convert this, E4P into cetoheptulose 1,7-biphosphate. 1,7, sorry, it's not bi, it's phosphate. And we do that in the presence of an enzyme, and also DPAH, which is dihydroxy acetone. Acetone salt. Okay. So we do that in the presence of an enzyme, same enzyme, aldolase. So we do it in the presence of aldolase enzyme. We convert E4P and DHAP into this. This cetoheptose, ceto 1,7-biphosphate gets converted into cetoheptose in the presence of an enzyme called cetoheptose 1,7-phosphatase. Phosphatase is an enzyme. Okay, so for phosphatase. So this is an enzyme. So in the presence of this enzyme, this is cleavaged to form this cetoheptose 7-phosphate. So once we've got this cetoheptose, this cetoheptose again, so this cetoheptose loses 2 carbons. I mean, 2 carbons are not lost. In fact, I mean when I mean something is lost, I mean when something is lost, I mean basically we remove it. And how do we remove this? How do we remove? We remove it in the presence of a transketolase enzyme. Transketolase. So we remove it in the presence of transketolase, and giving us ribose 5-phosphate. So this is what you get, ribose. So you get ribose 5-phosphate. So the structure of this, I don't think I have to remind you. Ribose is an aldopentose. Okay, so erythrose and triose and ribose, arabinose. You think about it. Ribose sugar is an aldopentose. So ribose 5-phosphate. And this ribose 5-phosphate again is converted to ribulose. So this guy is converted to ribulose. Ribulose 5-phosphate. And you can do that because this is an aldose and this is a ketose. So you can convert an aldose into ketose. There are a lot of methods with that. Ribulose 5-phosphate. And we do that in the presence of an isomerized enzyme. It's called phosphopentose isomerase. When I mean ACE, I mean it's the name of an enzyme. Okay, so this enzyme basically isomerizes. So these two are basically isomers if you think about it. Because aldopentose, when I talk about ribose 5-phosphate, I mean ribose is an aldose, right? It's an aldose. So this is a version of this ribose. It's a ketose. So we're converting an aldose into ketose. They have the same formula. They're isomers of each other. So we do that in the presence of phosphopentose isomerase, because this actually isomerizes phosphopentoses, specific enzymes. So this complex process happens in plants. That's one of the amazing facts about biology and biochemistry. Okay, so we get this ribulose 5-phosphate, and once we get this ribulose 5-phosphate, that's the victory. And we can again phosphorylize this. We can phosphorylize this to form ribulose 1,5-bis phosphate. And this is RUBP. So by this complex mechanism, we actually regenerate RUBP, which is used in step number 1, carbon fixation. So this is very complex, I can understand. Most of you might find it very, very difficult. So I too find it difficult. So let me tell me just a recap of what happened, what I did. Okay, so what I did is basically the following. I took this dihydroxyacetone phosphate, which is called as TPAH, and G3P. Now, in the presence of an enzyme called aldase and 1,6-biphosphatase, and I converted it into fructose 6-phosphate. So this is the structure of fructose, this is the structure of fructose 6-phosphate. Next, I reacted this fructose 6-phosphate. I made it to lose 2 carbon atoms in the presence of a transketolase enzyme to form erythrose 4-phosphate, which is the following. It's called E4P, this is called F6P. This is the structure of D-erythrose, and this is the structure of erythrose 4-phosphate. So next we took this erythrose 4-phosphate and we reacted it in an enzyme called aldolase, and we converted this into cetoheptose 1,7-biphosphate. Okay, so this is a heptose basically. So this has 7 carbon atoms. It's called heptose. Okay, So we took this ceto-1,7-heptolase and we cleavaged it in the presence of ceto-heptose 7-phosphate.